This one. All right. Okay. Let's continue our stream. Okay. Uh, our tutorial session. We go to chapter 5. So we spoke about. Right now we are talking about variable DC, variable speed DC drives. If we're looking at single phase DC drives, we've seen single phase semi converter drive. We've seen single phase fully controlled rectifier type. Now let's look at the dual converter. The dual converter is two. You have your, so you have an armature here, right? You have an armature here. I'll connect this part. I'll connect a rectifier to this part here in rectifier mode like this. So I have it like this. And over here, I'll connect an inverter. So inverter just means that opposite side. That's it. So let's go to the diagram. You get what I'm trying to talk about here. So this is how it looks like. So you can see that this is the normal one we know. This is the normal fully controlled rectifier we have, right? Fully controlled. You can see it here. Then you connect another one but anti-phase, so opposite that one. So you can see here. So that means that I will be able to supply positive and negative. You get it? So with this type of connection, I can run in all quadrants. I can run the motor in quadrant 1, quadrant 2, and quadrant 3 and 4. So if I want to run in quadrant 1 and 4, I use converter 1. If I want to run in quadrant 1 and 4, I use converter 1. If I want to run in quadrant 2 and 3, if I want to run in quadrant 2 and 3 here, I'll use converter 2. Right? If you run both of them at the same time, there will be something called the circulating current mode. But usually in a run, you make just one run. So we know the formula for the output voltage for this, right? Of a fully controlled rectifier. Now for a fully controlled rectifier, V naught is what? 2√2V over pi. 2√2V over pi. And this region here, because it's negative, so this one becomes negative 2√2V over pi cos alpha. So I'm going to cos alpha 1 for converter 1, cos alpha 2 for converter 2. Now, at the instant when I'm changing over from converter 1 to converter 2, these two become equal. That means that at the instant of changing from converter 1 to converter 2, 2√2V over pi cos alpha 1 will be equal to 2√2 negative 2√2V over pi cos alpha 2. So you can see that this will cancel this and this. So I believe it was cos alpha 1 is equal to negative cos alpha 2. Cos alpha 1 is equal to negative cos alpha 2. Meaning that negative cos of an angle is equal to what? Cos of the angle plus pi, I think. Yes. So I'll get cos alpha 1 being equal to what? Cos alpha 2 plus pi. So we're left with alpha 1 is equal to alpha 2 plus pi. Alpha 1 is equal to alpha. Let me check if I've written the correct formula here. Oh, I think it's minus rather. Let me see. Okay, so it's rather pi minus alpha 2. Sorry. Rather pi minus alpha 2. Minus cos alpha is equal to cos pi minus alpha. So I'll get cos alpha 1 is equal to what? Cos pi minus alpha 2. Alpha 1 is equal to pi minus alpha 2. Alpha 1 plus alpha 2 is equal to pi. So it means that at the instant of changing from one converter to the other, the delay angle for this plus the delay angle of this should be equal to pi. So there we have it. So let's think of a question like this. Let's see this question. It says that a separately excited motor is driven by a single phase dual converter. The motor has an armature resistance of 1 ohm, a field constant of 3 volts rad per second. The AC voltage source is 480 volts. Assume that the load torque is bidirectional and equal to 120 Newton meter in either direction. The trigger angle of converter 1 forward motoring is 30 degrees. Regenerative braking is applied. See, we said that we mentioned that it's a dual converter, right? Dual converter here. I have the rectifier here. I have the inverter mode here. Correct. Now they say that it's a bidirectional torque load. So like this here, let me see the value of the bidirectional of the torque. 120 Newton meter. So 120 Newton meter here, 120 Newton meter here too. Are you following? Yeah. And don't forget that because we said that, so when it's running in this first quadrant here, it means the first converter is working. Converter 1 is used for quadrant 1 operation. Quadrant 2, it means this one will be working here. That's the difference. So you initially say it's running on this characteristics here like this, right? Now, when I apply the braking, it shifts to this direction here and runs on its characteristics. Are you following? So this one is converter 1 working, this one is converter 2 working. Okay. Now even as I have the rectifier here, I have it something like this. I have it like this. Just draw it opposite direction. Like this here. Now they say that what? The triggering angle for forward motoring is 30 degrees. That's converter 1. The alpha is what? 30 degrees. A regenerative braking is used. Calculate the voltage that must be applied to the motor to reduce the initial braking current to 3 times the current drawn by the motor before braking is applied. So before braking is applied, let's find the current in the motor. So before braking is applied, let's find the IA, right? It's equal to what? K phi IA. IA is torque over K phi, torque is 120. K phi is what? K phi was given as 3. K phi was 3, right? 3 here. Over 3. The current is what? 40 amps. This is like the current, we call it IA1. That's the current flowing in the motoring direction. Now they say that what we want to during braking, we want to reduce this current to what? 3 times the value. So IA2 is what? 3 times IA1. That's what? 120 amps. And notice that since it's occurring in the second quadrant, this current is what? Is a negative current. This current is a negative current. So I'm going to find the voltage. Find the voltage that must be applied to the motor to reduce the initial braking current to 3 times the current. So I know that E is equal to what? E is equal to V minus IA RA. So V is equal to E plus IA RA. Right? I know IA, negative 120. I know RA. I don't know E. But know that I can find E for the motoring. The E for the motoring will be the same as the E for the braking because when I switch, the speed does not change instantly. So because E is equal to K phi omega and speed does not change instantly, it means the E2 will not change. Do you get it? So that's the principle here. So that's the principle. So first let me find E1. E1 is what? What do I have? I have what? Let me see what I have here. Okay. E1 is what? I can find my E1. E1 is V minus IA RA. And the voltage supplied during the forward direction. I can find that voltage here. As V naught is equal to 2 root 2 V over pi cos alpha. I know the V, I know the alpha. I can find the voltage supplied during the forward direction. And that V is supposed to come here. Do you get me? So let me do it here. So I'll do 2 root 2. So I'll find that V here. 2 V over pi cos alpha. Right? Minus IA1. IA1 was 30. RA1. That'll give my E1. And we say E2. Then we say that now here the E2 is the same as the E1 because the EMF does not change instantly. So let me make V the subject here. So V is equal to E1 plus this. But the current must be negative and 3 times. So negative 3 times 40, you can see it here. E will be the same E, so I can find my V2. That's it here. So that's what I was trying to show. We can find our voltage for the second case with this current negative 120 here. So once I have that voltage, that's the voltage supplied here during the braking. That's the voltage during the braking. So I'm supposed to find a triggering angle for that one. So once I know V, I can just put it in V is equal to negative 2 root 2 V over pi cos alpha. V is equal to what? Negative, because it's acting as an inverter, is negative 2 root 2. Negative 2 root 2. So you put it inside here, find your cos alpha here. That's it. That's it here. Okay, so that's it. Now the example 10 says that for the motor in example 9, assume that it is necessary to keep the motor at holding after TVR braking is applied. That's terminal voltage reversal braking. Calculate the triggering angle of the converter. Calculate the triggering angle. So we know that you want to keep it at holding, right? So speed is what? Speed is V over K phi minus RATE over K phi squared. Holding means that speed is 0. It's not moving. It has been held. Speed is 0. So V over K phi is equal to RATE over K phi. So let me find the voltage at holding. Voltage at holding. Do you get it? The voltage at the holding condition, V this times K phi. That will give me what? RATE over K phi. So I'll put in the values. My RA was 1, C 120, K phi 3. That's 40 volts. So V is 40 volts. So this is the voltage that will be applied during the holding condition. The voltage that will be applied during the holding condition. Okay. So that's the voltage here. That will be applied during the holding condition here. 40 volts. But we're looking at what? Terminal voltage reversal, TVR method. Terminal voltage reversal, TVR. So what do? It becomes negative. Or when you're putting the torque is negative. Keep it in your mind. So once that torque is negative, once here is negative, it means I'll get this to be negative 40 here. And it makes sense because it's terminal voltage. So I just equate this negative 40 to negative 2 root 2. Because during braking, the second converter that's working. So negative 2 root 2 V over pi cos alpha. Now find my alpha. And I'll compute my alpha. So alpha will give you this here. Alpha will give us that here. That's it. So that's it for the single phase converter drives. Single phase converter drives. Now three phase two, we have three phase semi-controlled. That one, so is that the formula? You can see the formula here. 3 root 2. So you have to just memorize the formula here. Then we have three phase full converter. That is the formula. So yeah, the formula is okay. So that's it. So you have to just read all this parts here. Or just read all this parts. Let's just read all that part. Okay. So now let's see what we have. Let's see what we have here. We said three phase fully controlled FC. V naught is 3 root 2 V over pi cos alpha. Then single phase semi-controlled is what? 3 root 2 over 2 pi V 1 plus cos alpha. So it's a formula work. Okay, let's move on. 750 horsepower, 250 volts, 120 rep per minute DC shunt motor. It's connected to 208 volt 3-phase 60 hertz line. So I have a 3-phase. So let's try to draw it. Always let's try to make sense out of it. So I have it like this, right? Connected to a 208 volt line, driving a 3-phase motor. The rated voltage of the motor is 250 volt. This is the rated voltage of the motor. Rated speed of the motor is 1200 rev per minute. This is the voltage drawn from the line. This is a frequency. Using a 3-phase fully controlled, so we know the formula we'll be using. We'll be using V naught 3 root 2 V over pi cos alpha. The full load current, so the full load armature current, IA full load, is 2500 amps. And the armature resistance is 0.004 Ra. Okay. Assume that conduction is continuous. Calculate A, the firing angle required under full load conditions. Required under what? Full load conditions. Full load condition means that what is drawing rated current, drawing rated voltage, running at rated speed with rated torque. So that's it. So let's see. So find the firing angle at full load condition. So at full load condition, the voltage of the motor is what? Is the 250 volts that is drawing. So we know that V naught of 3-phase is what? 3 root 2 V over pi cos alpha. So the V here is the supply V 208. The V here is the rated voltage. Because let's say rated condition, so 250. So I'll get 250 is equal to 3 root 2 times 208 over pi cos alpha. And I'm supposed to find the firing angle cos alpha. That's it. So just input cos alpha. So you find the value for the cos alpha. The B says that find the firing angle so that the motor will run at what? 600 rev per minute at no load. Find the firing angle so that the motor will run at 600 rev per minute at no load. So we know that for every motor, E2 over E1 is equal to what? N2 over N1. So N2 is 600 in this case. Rated speed is what? 1200 times E1 should be equal to what? E2. The firing angle so that the motor will run this at no load. At no load. At no load. So let me find my E1. E1 is what? E1 is the EMF, right? EMF at the rated condition. So E1 is equal to V minus IA RA. The rated voltage is 250 minus IA. IA was 2500 times RA. Then RA was what? RA was 0.04. So 0.004. 250 minus 2500 multiplying 0.004. So that'll give us my E to be what? E1 is 240 volts. E1 is 240 volts. E2 is half of this value. So E2, that is the EMF at the new speed, is half of 240. That's what? 120 volts. 120 volts. So that's the EMF here. But they say what? This speed at no load. At no load, we know that E is equal to what? E is V minus IA RA, right? But at no load, IA is 0. So at no load, you write that at no load, E is equal to V. So you mean that the voltage to run at this speed is also equal to, so the voltage here will be equal to 120 volts. And I must find a firing angle. So once I know the voltage, I will use the formula. Once I have my voltage, I can use the formula, this formula here, to compute my. So I know that V naught is what? V naught is 3 root 2 V over pi cos alpha. V naught is the same as the E because it's no load. So that's 120. It's equal to 3 root 2 V square root over pi cos alpha. And I'm supposed to solve for my alpha. So this was the first case, rated condition. So you find alpha rated condition. Second case, we found our 120. So that becomes at no load. So at no load, E is equal to V. So this V becomes a V driving the motor. So I'll put it in the equation. And I'll get this one here. The C says that what? The firing angle required so that the motor develops its rated torque. The firing angle required so that the motor develops its rated torque. What is the rated torque of the motor? What is the rated torque of the motor? We know the torque is what? K phi IA, right? Torque is K phi IA. Do we know K phi? No, we don't know K phi. So also, we know that torque is also equal to what? Power is torque times speed. So torque is power over speed. So rated power over rated speed gives us rated torque. Rated power over the rated speed gives us rated torque. So once I have the rated torque, I'm going to compute the firing angle at that rated torque. So once I have the rated torque, I'll find, hold on. So I'll find the current. So I know that, so here too, I'll find a new E2, right? I'll find E2 is equal to E1 multiplying what? N2 over N1. I know what my E1 was. I know N2, I know N1. So I can find my E2. Except over here, E is not equal to V because here there is a load connected to it. So I can't just, so I'll find my E by using what? I'll find my E. Find my E using E is equal to V minus IA RA. I have my alpha, I know my E. I want to find my V. V is what? E plus IA RA. E plus IA RA. Right? So now I know RA. I have to find IA. I have to find IA. At the rated torque. So at the rated torque means that rated current will flow through it. So even there's no need to even go through the process to find your torque set. Because we know our E here. We need V is equal to E plus IA RA. We need a V to find a firing angle. And because it's rated torque, it means rated torque is the same as rated current. Keep it in your mind. If it's driving the rated torque, it's because it's driving the rated current. So it means I can use the rated current 2500 here times my RA 0.004 plus my E, which I found here, 80 volts. So once I have my V, I can put it in the formula here to find my firing angle. I can put it in the formula to find my firing angle. So that's how you go about it. I'm going fast so that we can be able to finish everything so that you have time to go through. That's why I'm going fast. Okay. But if you don't get anything, just play back a little bit and then everything should make more sense. Everything should make more sense to us. Okay, so let's end here in this video. We'll continue in the next video.